have Anna Soter here from ETH. Anna got her PhD in Munich. Were you at LMU?
Yes,
okay,
LMU.
At LMU. And then was a postdoc at the Max Planck Institute for Quantum Optics in Garching and at the Paul Scherrer Institute. And she joined the faculty at ETH Zurich some time ago, where she works on the kind of amazing combination of cryogenics, superfluid helium, advanced trapping techniques, all in the aid of exploring fundamental particle physics. So looking forward to hearing about it. Welcome, Anna.
Thank you so much, Jack. And thank you for the invitation and for the hospitality. I had a really wonderful morning with all of you. And also remembering it was fantastic. So exactly, as you just said, oh, this is being transcripted.
Yeah,
okay.
That's for the people on Zoom. So, but if you like, everyone can see.
No, that's kind of funny. Sorry, that was just fine. I wonder if it's really understanding my accent, because Siri doesn't. So I have an issue. So in any case, as Jack just mentioned, I'm working on precision particle physics at low energies, additionally, so using exotic atoms and antimatter. So this is indeed a field which is a bit of a mixture of quantum optics and particle physics in some way. As you see, we are not actually doing the classical particle physics experiments by accelerating them and then colliding and measuring new particles coming out of these reactions, but we actually take particles created by accelerators, bring them to really low energies to rest, or capture them in atomic systems or other electromagnetic fields, and doing some precision measurements with them. But since I am a particle physicist as training, I have to start with a standard model to give some motivation to all of this physics. And we all know the immense success of the standard model, and most of it, your groups at Yale were actively contributing by the discovery of the Higgs boson, for example. But we all know that there are still questions that are remaining still within the theory. There are some cosmetic issues, what I would call them cosmetic issues, like questions we don't fully understand. For example, why do we have only 3 generations of particles, or why are there 3 generations? And why is it that we see this very clear hierarchy in mass, so there is now increasing mass, at least as of the charged leptons or the gluons. And as far as I know, there are neutrino people there, but it's a question in neutrino physics, but it seems that the same hierarchy is more likely to happen now in the neutrino sector. And we don't understand what is the explanation for this, because these are all parameters of the standard model, right? All the mass of the fermions are plugged in by hand and parameters of the standard model. There is now an issue with the Higgs being too light and causing some problems with the stability of the vacuum. There are some experiments which might be showing something with charged lepton flavor violation. So we have tiny anomalies in this sector. And maybe I could list still more things on this side, on the cosmetic issues side, maybe not breaking issues. But we have a rather big problem with the antimatter content in the universe. So there are cosmological observations which are causing issues for us right now, which are showing that there are not enough antimatter in the universe, which we don't understand if we simply look at data from particle accelerators. So wherever we do a reaction, we see that nature does not have a preference for matter or antimatter. This is described by the CPT symmetry in the standard model, and it seems to be valid in any experiments we are investigating right now. So this is one of the big questions. Obviously, gravity is not part of the standard model, and it's not quite known yet how to connect gravity with the rest of the interactions. And if we want to give an explanation to every cosmological observations, we need to find perhaps an explanation for dark matter and dark energy. So these all need new particles and well-known way to, or new interactions And the well-known way how one can look for this new physics is either on the high energy frontier, to do high energy collisions, obviously in using some particle accelerators and detector systems. I used to have a picture of the CMS detector here, but I changed it to Atlas because of most of your collaborators are from Atlas, I believe. And in these searches, the important thing is that by doing these collisions at para-electron volt scale energies, we do direct production of new particles. This is a direct search, right? We use the energy of the collision to create something new. In turn, this can be something new on the tera-electron volt scale. And it's limited by the collider energy. Now we have an alternative way to look for new physics. In particle physics, this is the indirect way, which is a complementary way to search for new interactions. So we can do this either by looking at some rare events or some tiny energy shifts in the interactions of particles. So, for example, I'm not telling everything which is happening in this front, but I'm telling the type of physics I'm involved with. We could look for forbidden decay. So in this case, it's important that any particle that's coming in the vertex and going out of the vertex is at standard model particles. And the new thing is happening in the loop. And the footprint of it is that the decay is, for example, showing some forbidden branching ratio or some forbidden decay by the standard model. So we look for this kind of decays in a certain group of experiments, or we can take particles, make them interact, and looking for tiny energy shifts in the interactions. So what I'm showing here is a bound system, and perhaps it's changing some virtual particles of the interaction, but we don't yet know. So this is more or less the idea of the experiments we are doing. The ingredients for it, obviously still starting with particle accelerators, because we need to create these particles to start with. So I'm working either at the antiproton decelerator facility of CERN. So this is the world's only low energy antiproton source. Or I have access to the world's highest intensity pion, continuous pion and muon sources at the Paul Scherrer Institute. So these are in two different locations, in Switzerland, in Geneva, and in Zurich, around Zurich. But besides these particles, we need also precision methods to investigate them. They are either ion traps, so we can trap them and see different things like the cyclotron frequency of these particles, or we investigate them with lasers. So we form exotic atoms and shoot lasers on them. Additionally, we need very precise measurements of energies, typically. And in the atomic scales, this usually means a frequency measurements. So we need metrology, or in certain experiments, we cannot do that. Then in this case, we need very precise calorimetry. So precise measurements of energy. And just to show why it's interesting in general to look at a simple atomic system, I brought up very quickly the hydrogen atom. I know that it's a textbook material, but for the sake of the students, hydrogen atom was teaching us a lot about modern physics, right? Already from the discrete spectrum, we have, we in principle needed to invent quantum mechanics. And this is how the Schrödinger equation was created. But just by the Schrödinger solution, you will not get to the precision of the 1s, 2s transition frequency, what we right now know about. This is 15 digits of precision in measuring energy of the hydrogen atom. And what people have seen is that you cannot ignore a lot of effects. Physics will start to appear already in the 5th or the 6th digit by taking into account the fact that the electron has a spin, and also it's a relativistic particle. Then quantum electrodynamics will give you the lump shift in the next digit. So this is all something that's appearing in the experiments. You start to have a better and better measurement, and you need to invent the physics which is behind it, right? It was always working in parallel to each other. The next step, the proton has a spin, cannot be anymore ignored. And also that the proton has a finite size. This is actually a very interesting question about the size of the proton. It means that it's not a point-like particle, point-like charged particle, but in principle, somehow a sphere, which is also not true. And what I wanted to show with this is that new and new physics blocked up as you increase the experimental procedure. And the hope is at first to measure a number. It's a very noble quest. But if you measure some anomalies, you either need to improve your theory, or maybe you are looking at something entirely new, so something beyond the standard model. And for this kind of experiments, you don't only need the precise theory in the precise experiments, and also the knowledge of all these colored fundamental constants, what I'm showing you. So actually, one such measurement is not enough. The hydrogen atom is not enough to look for new physics. And even multiple transitions in the hydrogen atom is not enough. You need to have many simple atomic systems. And this is how exotic atoms come into the picture. Exotic atoms are just like normal atoms, but instead of the electron or the nuclei, they are replaced by some other particle. And the nice thing about them is that many times they are two-body systems. The energy levels can be still very well calculated, but these exotic contributions, for example, finite size effect or any kind of hadronic effect, even QED effects, can be completely different depending on what kind of new particles are you using. We can replace, for example, an electron by any kind of negative particles. All negative particles will form exotic atoms for limited amount of times. We can replace an electron with a negative muon, we get muonic atoms. They are very sensitive to charge radii, for example, because the muon will orbit like 200 times closer to the nucleus than the electron did, just because of the mass difference. So very sensitive on size, nuclear size effects. Hadronic atoms, this is very tricky because if you do an exotic atom with a hadron, this will usually interact with the nucleus very quickly, and only in a few very special cases, one of them I will talk about, can they survive long enough to do laser spectroscopy. You can also replace the nucleus with a positive particle. You can form muonium. I will also talk about muonium. They're the mu plus, and an orbiting electron is forming an atom. Positronium is a very special system without a nucleus, if you want to talk about it like this. They are both, by the way, fully leptonic atoms. They don't contain hadrons, so they are a really interesting playground for bound state QED investigations. And then you have atoms where most of them are exotic in terms of particle content, like antihydrogen, antiproton with an orbiting positron. Yeah? While these atoms, what I showed you here on the right-hand side, maybe I should do this with this, can be created in easier ways. So normally these atoms that you are creating by stopping the negative particle in matter, they spontaneously will replace electrons via a charge exchange process. These kind of atoms, it's a reverse process. You need to take the positive muon or the positron, you stuff them in matter where they steal an electron from the matter. So they can spontaneously create, in principle, these two types of exotic atoms. When you create antihydrogen, you have to work much more because you need to mix two different charged plasmas together in ion traps in order to create antihydrogen. What do we do with these exotic atoms? So the oldest experiments they did with them was X-ray spectroscopy of negative particles taking over an electron. So this is that scenario when you have a negative pion, an antiproton, a kaon, a muon. What will happen in this case is the particle will take over the electron at the exact same binding energies what the electron had before. And from that state, it will cascade down in atomic states. during this process, it's OJ ionizing the rest of the electrons. So they are sending away the rest of the electrons and undergoing atomic states before they end up in the nucleus. So with hadronic atoms especially, you have this nuclear cascade with very characteristic X-rays. You can measure this X-rays, and this is how you know hadronic masses. So all of this, but the mass of the negative pion, for example, is coming from such experiments, or the negative kaon. What we do, or what we try to do, is that we are looking for transitions that can be probed by laser spectroscopy. It means that you need to find transitions that live long enough to be probed by lasers. And also, obviously, you need to find enough atoms to do this. And I was just drafting here, again, for the students who are not in atomic physics, what are the usual issues in this kind of experiments? You want to measure everything to the ultimate precision. And what is the ultimate precision is the natural line of the transition. Normally, it's just limited by radiative lifetimes in a normal atom. But if you have an exotic atom, then you will have different other issues. This exotic particle might decay. This shorten the state lifetime. Or this exotic particle might start to do some nuclear reactions if it's a hadron. So all of this will broaden the line width of this atom. So you will never get something as beautiful as hydrogen, just to remember that. But we still get to really nice precisions where we are already bothered by effects like the Doppler broadening. So if you have a moving atom, which is moving towards the laser light, it will see it blue shifted. If it's moving against, it's seeing it red shifted. So this will broaden your transition. If you start to collide with other atoms, this will also shift and broaden your transition. Also, we are suffering from external electromagnetic fields. Usually the case is that we are probing them with too strong lasers. So this is also causing all kinds of systematic effects. So what we normally want to do is to do precise spectroscopy of a narrow line. So we try to look for the narrowest lines and try to make it Doppler-free or Doppler-reduced by doing two-photon spectroscopy. This is a well-known method in spectroscopy where you are actually trying to cancel out the effects of Doppler broadening by making a transition which requires two photons. The absorption of two photons, which you send from left and from the right of the target, effectively canceling and only addressing, let's say, the non-moving fraction of the atoms. In order to address this kind of issues, you need to choose cold and low density gas targets normally. So low density and cold. So this is what we did, for example, with antiprotonic helium in the past, showing very quickly what happened at CERN. So we took antiprotons from CERN and we stuck them in a helium gas target. So as I said, for a precision measurements, that's what you want to do. Low density helium gas target. What happens there is the antiproton kicks out an electron and forming metastable states of this atom. So most of the antiproton will not end up in metastable states. Most of the antiproton will immediately send away the second electron as well and end up in the nucleus and doing the annihilation. But about 3% of them will end up in a very circular so-called Rydberg state. So they will end up in principal quantum number 38. This is having the same binding energy for the antiproton as the electron had before. And actually the orbit of this is still well within the Bohr radius of the atom. But it's a highly excited state. And if the state is circular, I don't go into the details, it can be metastable. It is because of the break-in degeneracy of the atomic levels with different L numbers. So there is large enough gap, for example, that these are not mixing during collisions. So you can keep, these orbits can remain circular for a long amount of time. without Auger ionizing the additional electron. But the natural life cycle is indeed this, that the atom will go through these states, as you see by the arrows, in the island of metastability shown by the red states. And at the end, eventually they reach a state where the Auger ionization become very likely. So the additional electron is away, and nothing is protecting anymore the ionic state from stark mixing and complete destruction, since the antiproton will find itself very quickly from a so-called elliptic orbit in the nucleus, which ends up in annihilation. So how do we do laser spectroscopy on these atoms? We are interfering this slow radiative process by taking one atom from a metastable state, and with a laser, we send it to this Auger-dominated, this short-lived state. So suddenly we turn some of the population into this short-lived state with a resonant laser beam. And when we do this, what we observe with particle detectors, which are surrounding this target, is that the number of annihilations are suddenly increasing. So this is the result of a pulse laser being on resonance, shooting on this target, causing some number of atoms to promptly annihilate in principle. And we see this as a resonant signal. And then we plot the number of laser-induced annihilations against the laser frequency, and we obtain these resonance curves. So in the best experiments, we indeed did this Doppler-reduced antiprotonic helium spectroscopy. We sent 2 photons from left and right, and we did it such that they were actually not having the same energy like it would be ideal, but we tuned them close to a real state, actually, to enhance the probability of this transition to happen. This 2 laser beam entered the cryogenic chamber here. This is where the atoms took place. We had to stop antiprotons for this experiment in this cryogenic helium target. Yes?
What kind of lifetimes and
oh yeah. So sorry, I didn't mention that the metastable lifetimes are around few microseconds. So it's 3-4 microseconds by the radiative lifetime of these states, right? So they can only do slow radiative decays from this state, and the Auger-dominated states are on the nanosecond and picosecond time scale. We usually try to probe something which is on the several nanosecond scale so that you have a more narrow transition. So the longer lived ones. But actually this is our signal. So because we want to see this prompt annihilation, so it's also important for us to see them going away. There are ideas to do metastable to metastable transitions, but it needs more lasers. You need to probe. But this is always our probing signal to destroy the atoms.
So then is that line shape that you were seeing?
It's antiprotonic helium.
And is there 2 lines, and is the width set by these lifetimes you were talking about at the Auger state?
Yes. So in principle, this is now close to the natural line width of the given transition. This is not the most narrow transition we have measured, but it's very close to the natural line width. And what you see there, the fine structure is for the same reasons as in a normal atom. But the funny thing is that the antiproton, like the angular momentum coupling is very strong. So you will actually never see such a split in a normal atom, right? So the angular momentum coupling actually to the electron spin, that's the funny thing. The angular momentum of the antiproton to the electron spin is creating the largest split here. And exotic atoms, by the way, are like this. They are always weird. Yeah.
And how long did it take to make that plot? How long did it taking?
So this is a scan over 1 day. No, not this. So this is, I would say, data taking of a full week, but you will see. You will see the resonance, like we just did this for precision, right? You want to collect some statistics, but you will see the resonance. They're usually scanning there and back. and you can finish one scan in 1 hour, and you are only limited by the speed of the accelerator, because we were receiving in every 2 minutes, right? Every point needs 2 minutes, but this is because of the accelerator, not because of the not because of the laser. So sure, yeah, so we did this kind of experiments, just wrapping up antiprotonic helium quickly. What do we do with this number? We have really precise measurements on the energies, right? And actually multiple transitions. And what they are related to in theory. So obviously the antiproton to electron mass ratio. And I mean, they also contain the charge of the antiproton. Oh, there should be a bar. Charge of the antiproton. So what you immediately get out of this is to assume that, you know, the charge of the antiproton is just like the charge of the proton. Then you can get the antiproton to electron mass ratio to the -11 precision, fraction of precision. Now, if you want to do a CPT test out of it, so that just to check whether CPT symmetry is real or correct, we need to have another measurement, because we have mass and charge of the antiproton. So what we do is that we also take penning trap measurements, which are in principle measuring the Q over M ratio, while these atomic systems are sensitive to the M times Q squared. So they are biting out a little bit different areas from the parameter space in terms of the systematic errors, and the two teamed up together can measure CPT symmetry to high precision. Finally, this number was mostly contributing not to the antiproton mass, because people like to do the CPT tests, but it was contributing to the electron mass for a long amount of time. Because this ratio, like the proton to carbon mass ratio, the atomic mass of the proton is very well known from penning trap experiments. And by assuming CPT, this number actually contributed therefore to the electron mass. But it's done better right now, again with penning traps. So the only physics that remains for antiprotonic helium is to put some constraints on new interactions. So I need to mention here that this is already not a playing ground anymore, because anti-hydrogen is there, right? Anti-hydrogen will also provide nice measurements on, we can have some argumentations on this, but what we work with, and it's interesting to mention, is the constraints on new interactions. So just by having a three-body system for antiprotonic helium, we can look for fifth forces on sub-angstrom length scales. So in this case, we can look for any interactions between the antiproton and the electron. It's actually very convenient because they are overlapping, the wave functions are overlapping quite a lot inside the atomic system. So you can be very sensitive to any kind of weird interactions.
This would be like a Yukawa correction to the electrostatic?
Yes, in principle, yeah. And there are some other more exotic things which I was never following up. So as you have seen, actually for these experiments, what we did in the past is that we tried to make the target colder and colder and less dense, because anything that was like collisions or temperature-related effects were just messing up the precision. So we didn't want to do any dense experiments. However, in my PhD, I started to get interested in this picture, what you see here. So what happens in principle, antiprotonic helium is looking very much like a helium isotope, or something from the outside. It's very much like a helium. There is a small distortion by the antiproton orbiting in the inside, but the electron is still on the one state. The atomic radius is very much the same as for the helium. There are some polarizing effects, tiny bit, but we knew already in the past from studying collisions of helium with the surrounding dust that actually pairwise potentials of helium and antiprotonic helium are very similar. So why is this interesting to put such an exotic atom in superfluid helium? There are a lot of people were excited to create not exotic atoms, but put real atoms in superfluid helium for various reasons. And they thought that it will be a really good environment for spectroscopy, a very clean and homogeneous environment. And actually they found something pretty interesting. If you put an impurity atom into superfluid helium, helium atoms are extremely close to each other. They are like 3 angstrom distance from each other. If you put an atom, and you just simply have polar repulsion from the outer electrons, will demand some more space for itself, if you want to imagine it like that. It will repel in many cases. There are cases where it's not happening, but I'm just simplifying the picture. Repel some helium atoms from its vicinity. So if you put an impurity atom, it will create a cavity or a bubble around itself, and it will sit inside of this bubble. Now, the interesting thing about this is that you don't have the atom anymore as a simple interaction-free system. What you will have is that you will have a lot of interaction between the atom and, in principle, the surrounding bubble. So vibrational levels of this surrounding bubble will mix with the atomic transitions. And what you will end up with is a system which is very similar to an organic molecule. By the way, that's the reason why a lot of these cryogenic liquids, it's not only helium that does that, but a lot of noble cryogenic liquids are doing the same thing. And that's the reason why they are scintillating, because you have a system which is in principle a many-body, looking like a many-body molecule, and has this all kind of vibrational levels that are broadening the transitions and shifting the transitions. Now, it's pretty exciting to think what happens to antiprotonic helium, which is in principle from the outside looking very similar to a helium atom. So as I mentioned before, pairwise potentials are extremely similar to the helium's pairwise potentials. And in principle, obviously, it cannot be part of any condensate, but maybe it can behave like helium-3 impurity. And let me mention that when I talk about that, such kind of interactions made the atomic lines extremely broad and shifted. I'm really talking about nanometers, like tens of nanometers. So you get like an organic molecule line shapes. Compared to that, indeed, what we found is that antiprotonic helium is doing something completely different. This double peak, what you see here, is actually one of the most narrow transitions we measured with antiprotonic helium in a low density gas target. These are all at 6 Kelvin. So all the green lines are measured at 6 Kelvin gas targets at different pressures. And obviously, the density is increasing in this direction. And what we have seen, or we expected, that if you go to liquid, which is also beyond this density, so when you start to do this measurement in liquid helium target, then you should, in principle, continue this trend. But what happened already in normal liquid helium, which you see with the blue, is that by the atomic transition lines started to shift, or kept shifting in principle, in the same way as they shifted in gas. So these are all on the same frequency scale. They are real measurement points just to overlay to each other. Right? In gas, you increase the density, it is shifting and broadening as you expect. But in normal liquid helium, the shift was still agreeing with the classical model, but the transition got more and more narrow. And we had a sudden narrowing at the phase transition, a sudden decrease in the line width. And we actually started to resolve again the fine structure. So the transition lines, what we measured at 1.8 Kelvin, become extremely narrow again. So what is happening? It is pretty exciting. I will also comment on the structure further a little bit later, but this will be a confusing discussion. One reason why it took actually some time to publish this paper. You see here how the line width is changing as a function of temperature. There is an exponential fall of the line width. When you reach this phase transition, this is normal liquid from 4 Kelvin to 2.17 Kelvin. When you reach the phase transition, you have a sudden drop in the line width and an increase again. I will comment a little bit later this increase. What we expected is that the sudden drop, and in principle, this whole trend is related not to classical collisions, but interacting with excitations in superfluid helium. So superfluid helium is a quantum liquid. The helium atoms don't have their identity anymore in the same way. It's an interacting quantum liquid, which makes it even more complicated. If this would be a Bose-Einstein condensate, we would understand what's going on, but it is not. Interestingly, what we know is that there is a bunch of excitations, photons, which are still present in the liquid just because of its temperature. So we have thermal excitations, and atoms are presumably interacting with these. The minimum what we measure is at the same location as where you measure minimum in viscosity in superfluid helium. By the way, this curve is then expected to fall back. I don't want to go to the very much details. This has something to do with antiprotonic helium being extremely sensitive to excitations in superfluid helium, and I'm very happy to talk about it after the talk. You want to know some details. I just wanted to show you that meanwhile, it's pretty important that the line shift seems to be rather much the same than for the gaseous state. So there is some way actually to extrapolate such a measurement to zero density. However, towards the end, so this is in normal liquid. So in normal liquid, the trend is still there. However, the trend is turning again, changing direction in superfluid helium. By the way, this part is not well understood. So I wanted to say we have qualitative understanding of what's happening in superfluid helium with this antiprotonic helium, but we don't have a quantitative understanding because actually nobody knows the microscopic structure of superfluid helium. So some theoreticians are actually very excited about these plots because we have a surgical precision on something what we don't understand. Now it is up to them to figure out what does this really mean. Now, for me, the important part about this was just to have a note on this, that this measurement was teaching us some new techniques what we can use in principle in exotic atom research. Just from the fact that we can restore in principle the vacuum transition, so it seems to be that extrapolation still works. This tells us that one thing, these exotic atoms are still alive in high density targets. This was not very obvious. We didn't know if it's really the case. And high density targets are important because it means that we can stop particles in them. So this gave us a way to do pionic helium and kaonic helium experiments and different antideuteronic atoms we can investigate. So by the way, these antideuterons or detecting antideuterons might be interesting for the dark matter community. As far as I know, they are being created by the annihilation of dark matter. So if you measure the content of antideuteron versus antiprotons in different experiments are proposing this, you can actually tell something about dark matter creation. Now, why I'm interested in this experiment right now is actually one important part we learned from this experiment is that classical coalitions were not playing anymore a huge role in the way how antiprotonic helium behaved in the liquid. And I will return to this. I just wanted to show one slide about another exotic atom, what we discovered. After we made this measurement in superfluid helium, we knew that we can have a shot at trying to measure pionic helium, which is this system. pions are coming rather energetically from an accelerator, so you need a liquid to stop them. We made a liquid helium target, and we did laser spectroscopy, and we measured for the first time the pion being excited by lasers. So from this, you will get a precise measurement on the pion mass. But what I want to talk about in the rest of the lecture is muonium, because someone is sitting here who wants to hear about muonium. But I was asked to talk about antiprotonic helium, which is my old experiment. Now, why is muonium interesting? One thing is the good old laser spectroscopy argumentation. So this is a purely leptonic atom containing the first generation fermion and the second generation antifermion, the positive muon. Now, when we carry out laser spectroscopy on this system, what are we probing? We are probing bound state QED to high precision. This is a purely leptonic atom, no finite size effects, no hadronic effects. So we can gain fundamental constants like the muon mass or magnetic moment. We can test bound state QED and symmetries, and this in turn has a huge effect on other precision experiments like the muon G-2, which needs the muon mass as a plugin. So we are playing this usual game. We are providing precision measurements on certain natural constants and trying to figure out something about beyond standard model interactions. What I got interested in is actually studying the free fall of muonium, which is not only me who is interested in this, because we know in the exotic atom community that they are in principle very exciting probes for gravity measurements, because if you want to measure gravity with something different than proton, neutrons, or electrons, so normal matter, you still need to have neutral objects. Nobody managed to make a gravity experiment with something which was charged and tiny additionally, right? So you have a particle, the standard model particles are typically charged except for the neutrinos, but you have more serious issues with neutrinos. So what do you want to drop there in the standard model? It is very exciting, obviously. Yeah, so I need to point out that ordinary matter is just a small fraction of what we have in the standard model in terms of that it's built up from UND quarks and electrons. Right? This is mostly ordinary matter. Obviously, you have virtual particles all around the place, but these are the main building blocks. Now, my colleagues at CERN, since more than a decade, are interested in dropping antihydrogen. And actually, very recently, they succeeded. And that's the result. So the antihydrogen is dropping down. So far, that's what we know. And these are first generation of antifermions. So in some way, we know that, like, not to a high precision, but we just observe that matter and antimatter in the first generation more or less falls in the same way. Now, I want to point out something here, which is a little bit on the theoretical side. How do you get the mass of a hadron? Like the proton mass. You take UND quarks, but we all know that it's a full branch of virtual quarks and gluons, which are actually generating the mass of the hadron. So it is all in the field, all in the interaction. And so 99% is coming from a process which we cannot fully model as of now or calculate. However, in muonium, the elementary masses, we have elementary particles, the electron and the muon, and the elementary masses are dominating the muonium mass. Actually, the uncertainties in the muon mass are right now at the level that the binding energy of the electron starts to be important, and this is QED, right? So one argumentation of dropping muonium is that we are dropping something which is very fundamental, a very clean coupling to standard model parameters. These are standard model parameters, the muon and the electron mass, of gravity versus the hadron sector. So let's say if there is something different with leptons versus the quarks, we might be able to see it. Another interesting thing we might think about is that the muon is also a second generation particle, well, actually a second generation antiparticle. And there is this rather exciting hierarchy in terms of mass. So we see that the generations of particles are in principle exact copies of each other. The only difference what they have is the different masses. So it would be rather exciting to take a standard model particle from a higher generation and see whether they still fall in the same way. This is something where we don't even have indirect measurements. So is the equivalence principle, the weak equivalence principle, still true in the second generation? In principle, on the theoretical side, it would be much more easy to introduce some new physics, which is about generations, so some new physics different for the generations versus matter and antimatter disparities. So that's the motivation. We now have some discussion with theoreticians who are also trying to estimate what will this mean in terms of some other extra interactions. Yeah. So we try to do this measurement. I will be a little bit fast here. I just wanted to show that obviously this would be very shy compared to the weak equivalence principle test using normal atoms, which has been conducted in since more than 100 years with increasing precision. I wanted to point out one thing is that the formulation of the weak equivalence principle, which is telling us that any kind of experiment, what you carry out on the surface of Earth versus an accelerating lab, should give the same results. And now this is encompassing a lot of different theoretical statements. So universality of the free fall or experimental consequences, if you want to take it like this. Universality of the free fall is just one consequence of the weak equivalence principle. You then have the local Lorentz invariance and local position invariance. And there are a completely different group of experiments which are investigating local position invariance. This would be the universality of clocks and lack of variation in fundamental constants. So I'm just showing here the most well-known experiment. So this was tested with normal macroscopic scale bodies and also with atoms. So all kinds of scales it was tested. But if you want to carry out a weak equivalence principle test and really to draw muonium atoms, you will run into a huge difficulty. You will realize that it's not possible with existing muonium sources. How do we create muonium? We take muons from an accelerator beam and we direct it into a slab of aerogel or some other kind of porous materials, which is rather important because the muon has to turn into muonium by picking up an electron from matter. So that's the way how it becomes an atomic state. But then the atom afterwards has to diffuse to the surface, which is almost impossible during their short lifetime if it's bulk matter. So you need to use some porous material to actually get them out of the surface and to do some experiment with them. Now, if you do this in a slab of aerogel, the problem is you will get a thermal atomic beam. And if you additionally realize that you want to measure gravity, which is an extremely exaggerated picture here, you will need to measure gravitational force on the below nanometer scale because of the short lifetime of the atoms. So this did not seem feasible at all with such kind of atomic sources. The reason why we think it might be possible now is that we created a cold atomic beam, a high quality atomic beam, by converting muons into muonium in a thin layer of superfluid helium. And this atomic beam might be, we think at the moment, might be amenable to atom interferometry, which is then a sensitive tool to measure this kind of inertial forces. And this is the method how we do it. I have to point out that this relied on 4 previously unknown physics processes in superfluid helium. So I'm telling you the final experiment, how it looked like, but it was some kind of a struggle. So we stopped muons in a slanted beam. So we actually direct the muon beam down, and we stop them in a slab of superfluid helium, where they create electrons as they ionize helium atoms while they are stopping. They create some electrons from the ionization trail, and they capture the very last electron they created. After a while, they are too slow to ionize anymore, but they can capture the last electron from this ionization trail and form muonium. Then something happened, which was quite unlikely, and actually before the superfluid helium experiments, we didn't know this will happen, is that this exotic atom was still small enough to have ballistic diffusion, absolutely no collisions, and reach the surface in a rather rapid times. So after formation, it spent some time with thermalizing, but it thermalized only below 60 meters per second, which are the Landau velocities. And afterwards, what we hoped, and at the end we measured, is that it will travel with this Landau velocity to the surface. Normal atoms don't do this. Normal atoms are too big when you put them in superfluid helium, and they will do all kinds of hydrodynamic effects. So people try to drag through ions, for example, in superfluid helium. They didn't measure Landau velocity because these are just too large, created too much hydrodynamic effects, which was slowing them down. But with the small exotic atoms, this didn't happen. So it could go ballistically to the surface after cooling down to these nice temperatures, by the way. And at the surface, another surprising thing happened. Due to the positive chemical potential that they have in superfluid helium, they were ejected in the surface normal, in the direction of the surface normal with rather large velocities compared to the perpendicular velocities. So this was then an atomic cannon, and we measured this kind of beams coming upwards by surrounding this cryostat with detectors in the cold, and we were actually tracking positrons from the muon decay and also measuring at the same time the electron which was left behind after the muon decay. So I will just, again, comment here very quickly what was the physics behind it, what made this possible. The most important point here is that we are at very low temperatures in superfluid helium, below 200 millikelvin. I know that this is not the lowest temperature what you can get, but at these temperatures already thermal excitations are very sparse. So muonium can actually spend a lot of time not meeting any of these thermal excitations, with an estimation of 5 such scattering happening in a second at these temperatures, which means that they can really travel through the liquid without being bothered by any scattering. And the surface ejection theory was based on some studies with hydrogen, deuterium, and tritium. So we just took muonium as a very light hydrogen isotope. And in order to make the experiment, we still need to figure out some things. Maybe we need to rely on quantum reflection, but I will not talk about it. I just wanted to show a little bit the data. So this is very fresh data a few months back that we measured the emission of this atomic beam upwards by actually surrounding this target with particle detectors. So the bumps are showing when the muonium atoms are passing by and happening to decay in the direction of these detectors. So these are all time spectra. They are showing the muonium moving in our chamber. And as you see that the bump is advancing, it's moving ahead because we are measuring in layer 1, 2, 3, and 4. This is just grabbing out some part of the data. From this, we could measure the velocity of the atoms, and we model this whole system with Monte Carlo simulations. So we have many of these curves. We modeled it with Monte Carlo, and we concluded the following. I show you now the result of different Monte Carlo simulations, what can happen in principle in these chambers. So what we call our atomic beam is now a superthermal beam, in the sense that in the horizontal direction, you have some thermal distribution, or in every direction, in principle, you have this few Kelvin thermal distribution. But in the upward direction, you will have a peak of around 2.1 or 2.2 kilometer per second versus the thermal velocities of 70 meter per second. It's a very well-directed beam. The thermal beam at 50 Kelvin, which is, by the way, never happening. You cannot get muonium out of a 50 Kelvin source. They will just stay inside, stick to the walls. But if that would be a thermal beam, it would have a completely different characteristic. And this is what you see in Monte Carlo simulations, that we see an agreement, not with the thermal beam, that would be the orange thing, but on all of our time spectra, we see a rather perfect agreement with this so-called superthermal beam. What does this mean in turn? If you look at the velocity distribution of the atoms, this is the Maxwell-Boltzmann distribution. This is something what we can produce at room temperature. It's the 300 Kelvin equivalent curve. And what we have right now from muonium is this 2.2 kilometer per second and rather narrow velocity distribution is overlaid here with the blue. So this is a pretty high quality atomic beam. Additionally, we measured how many of such atoms are we creating per stop pion. So if there was a possibility to look towards the target with a pair of detectors, and what you see here is the time spectra of muonium being emitted from the target. The red one is when you don't have any superfluid helium in the target. The number of muonium or muons are constant. They are staying on the floor. But when muonium is leaving the target, you measure this curve. And actually, we are estimating around a 10% emission of each stop muon, which is actually comparable to the best room temperature sources. So what we try to do with this experiment, and I'm somehow, because the temperature, I'm being a bit slow, I'm sorry. Yeah. So what we try to do with this experiment is to create, actually in the first step, a horizontal atomic beam, because this is what we need for gravity measurement. I will comment how we are trying to do this. And then we would direct this horizontal beam to a pair of gratings, which will create a vertical interference pattern. And the effect of gravity will appear as a phase shift of this pattern compared to an interference pattern made by light. So if you would use photons, you would get the straightest direction you can get in space-time from photons. They would create an interference pattern, and atoms which are falling in the interferometer will have a vertical phase shift compared to this. So we try to measure this vertical phase shift by using a masking grating and moving it up and down, scanning it up and down, and just simply count the number of atoms that can pass through. We do this because we don't have a good enough resolution to actually measure the interference pattern. We are using for the measurement of the number of atoms classical particle detectors, but they are pretty challenging because they have to be in a cryogenic environment. In order to differentiate that we are really seeing atoms and not just muonium, we need to also measure not only the decay positron, but the atomic electron. And we estimated, just by knowing the parameter of our atomic beam, we could estimate how this setup should look like. So we already know that we need to use, this is normal sensitivity equation. You see this is in principle just from statistical argumentation of measuring a periodic pattern and the phase of a periodic pattern. So how much acceleration are we sensitive to if we measure for a certain amount of time? Using a certain amount of particles and creating an interference pattern with a C contrast. Now we see that in order to overcome this difficulty that the atoms are living really short, so we can do this measurement only for a couple of microseconds, we need to use a grating period which is really tiny. So you want to have these bumps really tiny, around 100 nanometer size. And you have to ensure that you have a lot of atoms on your interferometer. And additionally, that the quality of the atoms are high. So you have a really nice and parallel beam so that you can have a high contrast for a longer region in the interferometer. So we are estimating right now that we can tell the sign of G with our presently existing atomic sources within 1 day, and maybe we can hope for a 1% overall sensitivity if you do the measurement coming out. So we have enough, at least enough atoms to do this, but we still need to overcome a lot of difficulties. I'm skipping this. This is just about calculation of the interferometer parameters. What I want to show you is actually just open discussions. If someone is interested in the techniques, what we are doing right now, this is all new and still open. I mentioned to you that we need to create a horizontal atomic beam, which is pretty challenging. You need to measure the reflection of the atoms. You either need to do some reflection, which I would try to avoid by converting them directly in a vertical helium source. So what does this mean? We try to integrate the first grating of this interferometer with a microfluidic grating, in the sense that we try to prepare trenches in the backside of our nanoscopic grating, which is actually measuring gravity, that's in the front here. We try to do these big trenches in the backside such that we can start muons in these trenches when they collect superfluid helium in the backside. So the main function of the trenches is that via the capillary effect, they will collect helium. I'm demonstrating it here with the first model of a prototype collecting some alcohol in this case. So it is kind of working with alcohol. We hope that it's also working with superfluid helium during the beam time this year. We actually modeled the surfaces. That was really funny to do this modeling with finite element simulations of what should be the trench width and depth and so on, in order to still make the capillary effect work for this. And atoms would be emitted from the front side, which should be like flat enough, since we have only tiny, tiny slits of silicon nitride grating to produce a really flat and vertical surface. This is our idea to do this. If you have, I heard that some of your groups have experience with microfluidic devices, so it would be nice to hear your opinion, especially how you do the modeling. I still don't know if it's working. We just have a model and we hope in some calculations. The second thing we need to do, call detectors. I'm jumping this through, but this is also pretty exciting. The hard thing to do is to count electrons. If you want to talk about it, how to count really low energy electrons in a chamber which is coated with superfluid helium, this is a hard thing. The idea is that we need to accelerate them towards the detector. You cannot measure them at electron volt energies. So we need to accelerate them at least to the kilo electron volt regime to measure them with classical particle detectors. At room temperature, we would have more options, but we need to work out some new techniques in the cold. We are investigating, for example, superconductive nanowires as a possible option, and some really exotic crystals that can measure with a very low threshold these kilo electron volt electrons. So about this, I'm also happy to talk. Then the idea for the grating would be actually a monolithic silicon raft, which is done by the UCN community. And I'm actually trying to do fusion bonding of a freestanding silicon nitride grating, which would contain these tiny 100 nanometer slits. Right now, the idea is that we do a fusion bonding of these two silicon devices to have a monolithic but split silicon interferometer. And we are thinking so far only theoretically the works to stabilize and scan this device. We have a small optical bench where we started to make some trials. But if any of you have experienced how to do nice vibration stabilization in a cryosat, I will be happy to hear about. This will be how the whole device is looking like right now. This is an absolute concept. If you ask me 2 years from now, presumably it will look different. But that's the idea so far, that we make this vertical grating work, which has superfluid helium in the front, we convert the muon to muonium there. We have these two following gratings, and we do the detection. So we move this last grating, yeah, this is the masking grating, and we move, we make particle detection in a decay volume. And that's a very last slide. That would be the impact of the measurement, a little bit more overarching impact. So very obviously, it's not only the gravity experiment you can do with such a cold atomic beam, but you can do laser spectroscopy much better than we can do right now. So with 1s2s laser spectroscopy, this is just a very preliminary estimation. But in principle, the fact that you have the atoms in a tiny volume, you exactly know where they are, just because you have them compressed in phase space. You can focus your lasers better, and you can address just simply more atoms. So you increase the statistics by a factor of 1,000. In the same time, transit time broadening will be about the third, and second order Doppler shift in the same way will be about the 10th, so the square of this. High brightness muonium beam. I just very quickly mentioned that if you have muons in a well-defined location, even if they are muons or muonium and they are slow, then you can actually create perhaps a really interesting source for muon colliders, but definitely some very interesting source for solid-state physics investigations like muon EDM. So we use muons as a precise spin probe to implant them in different matter, and for these low energy muons are really so. So these are applications in all fields, which is maybe not so close to yours, but in any case, such an atomic beam by itself is rather exciting. With this, I thank you for your attention and sorry for a few minutes of delay. Started to fall asleep, guys, so you can ask more questions. It's hot. Sorry.
Questions? Ron?
On slide 38, what were the units?
30 what?
38.
8.
Yes, what were the units on?
This is millimeters. Sorry, it's not inch. Or something. So yeah, it's about 10 millimeter in between the gratings. This is like the optimized distance. So one can really make a monolithic silicon device in these dimensions.
Questions?
I guess, so yeah, great talk, very interesting. So do you have to worry, you talked a lot about the sensitivity of this really beautiful stuff. What about background forces from surface interactions if you're flying next to silicon nitride?
So the nice thing is that all the surfaces will be coated with superfluid helium, which is nice, but also annoying. So I tell you why is it nice. One thing is that, yeah, you need to worry about charge up usually. Yeah, you have particles ending up there, charging up the grating. And if you have electrostatic forces, then this will change the game, obviously. One good thing is that you are working with a hydrogen atom. Yeah, it's a muonium, but it's a hydrogen atom, so the polarizabilities are very low. That's one thing. The other thing is, and it's a small atom, the other thing is that you can metallize surfaces. So the grating itself can have metallized surface. And additionally, what I unfortunately measured now is that there are free electrons, or there is a conductive layer in principle on top of superfluid helium as well. So electrons can move rather freely the surface of superfluid helium. We can talk about that, but I'm hoping that this charge-up effect will not come.
Okay.
Or we can avoid it.
If I can ask a question,
Yes.
in the antiprotonic helium, why is the line width so nice that the line width drops when it goes superfluid? Why is it turning around again when it gets even colder?
So the intuitive explanation is like nobody can calculate why, but the intuitive explanation is that you have excitations, and the number density of them is changing, but also the energy of them, like the average, like you know the dispersion curve of superfluid helium, obviously, and then as you change the temperature, you have different number of protons and phonons, like in the protons are only there around 1.5 K and above, right? The number is really low, around 1 K already. Mm-hmm. But in this regime, we have protons, phonons, and if you know the macroscopic Androni-Kashvili experiment, which is about viscosity. You in principle measure the collective effect of these excitations as a function of temperature. And there it is important how long they interact with the disk, with the rotating disk. And what is the number density of these excitations which interacted with this? Yeah, they explained it with the two fluid fraction in the old time and so on, but this is about excitations and interaction length or interaction times. And what is happening is that around this 1K, that number of excitations dropping down, but they are also lower in energy. So they spend more time with interacting. Like that's my intuitive picture. And that's why some theoreticians try to do this. But that's why also you have such a minimum exactly at the same temperature in the Androni-Kashvili experiment. But what then happens is that number of excitations gets really, really low, so you have a fall down again, which was not measured by us because like after this, you should have a sharp fall down, but we never had a low temperature experiment for this. So I don't know if it's true.
Okay, well, let's thank Anna again.